device in order to produce some type of improved current driver or power amplifier. And in the circuit to do that is specially called a push-pull or complementary BJT amplifier. So this is a suggested schematic of a basic push-pull amplifier. And the NPN is basically attached to the collector is attached to a plus battery, and then the complementary device is a PNP transistor. You notice the emitter is flipped upwards so that the emitter basically connects directly to the emitter of the NPN device. And then the collector of the PNP is attached to a minus 10 volt, and basically just a dual battery supply. The bases of the two transistors are tied together, and this does the out of op amp. It's basically a current driver, and it's attached between the op amp output and the load resistor. So understanding how this amplifier works, Lisa gets into designing it. There are no resistors basically in the network to actually design. So when the op amp, following the text, when the op amp output is positive, the NPN device turns on, and it goes current in here, and then when the input goes negative, the PNP device turns on. And so that switching between the NPN and the PNP as a sign where the input goes from positive to negative. Now the idea of the push-pull then is that the NPN device delivers current to the load, and then the PNP device pulls the current from the load. That's where we get this term push-pull between the two devices. Now basically, this is you notice that this is the first time we have two different transistors in NPN and PNP in the same circuit. So if you analyze the circuit, you start by treating it almost as a diode on and off question. So how do we respond to this first question here? In both of the VGTs, the QN, PN, and the QPNP, they both be on simultaneously.
Either you're supplying positive voltage to both transistors or negative voltage to both transistors.
It's positive or negative voltage, however, what's involved in turning either transistor on? What's the requirement to turn on?
0.7 volts.
So we need 0.7 volts. We need 0.7 volts positive for the NPN, and we need 0.7 volts negative for the PNP device. So the question is, can we supply 0.7 volts positive and negatively simultaneously? And that's what I'm asking, can we both be on at the same time? If they can both be on, then it's saying that we can apply 0.7 volts minus 0.7 at the same time. And in terms of the treating it as a diode problem, it basically means you have a positive and a negative battery connected to each other. And then you have issue, so it's not allowed to have a plus and a minus 0.7 simultaneous. So to respond to that, it's basically, of course it's saying never, but we still need a logical reason for making this conclusion. So the reason we give, one version is that the base emitter of the NPN requires 0.7 volts. And emitter base of the PNP also requires 0.7 volts. And therefore, for them both to be on, we have both of the bases connected together. So, for them both to be on, the NPN needs 0.7 volts across it, and the PNP needs 0.7 volts from the emitter to the base. And it's not possible to have both those PN junctions forward biased at the same time. So basically the default then is that the PN junction and the base emitters of both transistors, they require opposite polarity base emitter voltage to turn on, and the input being, if it's some kind of sine wave, it can't supply plus 0.7 and minus 0.7 simultaneously, so they both cannot be on at the same time. And the purpose of adding the PNP is because when the NPN turns off, the PNP supposedly turns on. So this diode contradiction is here, is that there's a contradiction between both transistors being on because of the different base emitter voltage. So if the NPN is on, the PNP must be on, and then the PNP is on, the NPN has to be off. And so the circuit acts almost like a rectifier circuit. Now how to respond to this question? Can both NPN and PNP, can they both be on at the same time,
Yes.
simultaneously? Now, we're not talking about turning on the power.
Right.
Okay, so when the circuit is operating, can they both be off at the same time?
If the voltage is less than 0.7, positive or negative.
Now, they have a the PN junction have what's called a cut-in voltage. And it's so 0.7 is the power curve will be on. They also have a cut-in voltage that is less than 0.7. 0.5 or a number of times. So the answer to this question is that if the NPN or the PNP base emitter voltages, if they go below the cut-in voltage, then both transistors will turn off, during that period of time. So the response to this question is that yes, both transistors can be off. When the circuit is operating, they'll be off at the same time, so simultaneously. And the reason justification is given is the cut-in voltages. One has a cut-in of minus 0.5, the other a cut-in voltage of 0.5. So when the input level is between plus 0.5 and minus 0.5, both transistors are turned off, and there's no output. There's no output signal from the circuit. And that's the cut-in voltage. Now, the problem then is that with this, it brings in one of the issues with this amplifier is that notes here, when the music or when the input is very low input, both transistors can turn off. And that's a problem in audio amplifier design. You most likely won't experience this in your stereos or any type of sound generating equipment because something has been implemented to remove that off time. But if you want to be aware that if the input level goes zero or very low, those transistors can turn off. And the technical term is given to this is called crossover distortion. So the other concern here is what happens to the input if the input is a pulse. So the input now, instead of a sine wave, it's a pulse. Will the pulse produce crossover distortion? Pulse is a fast rise and fall time.
With the near zero rising pulse?
Pulse goes to zero.
I meant like the time it takes to go from the bottom to the top of zero to zero.
Right. If you refer to the rate at which it falls from high to low, low to high, it should theoretically the pulse should pass through the cut-in voltage so very quickly. So we would say that maybe for the pulse there's little or no crossover distortion. The pulse through the amp, whatever reason the pulse is required. So, the word power amplifier, we get into why this circuit is called an amplifier. And the answer to that basically is that it's not an amplifier, even though the technical term calls it a push-pull amplifier, but this is not a voltage amplifier. Such as amplifiers will be studied. This is not an amplifier. The low input voltage, and its purpose is to move a current to a low. So the other kind of method of looking at this circuit is called power amplifier. You don't really amplify power. You can amplify the voltage, or you can amplify the current, basically. But the term power amplifier is also given to the circuit, but it's also still not a power amplifier. But even with that, this term exists in different versions of the circuit. Just keep in mind, it doesn't amplify power, it amplifies current or voltage, but regardless of that, you still refer to it as a power amplifier. So, at the top, if a small signal power goes in and we get a large power, and you're going to replace the word power with current. Put a small current in and a large current coming out. Where does this extra energy or current come from? With this circuit.
From the batteries connected to the VJTs.
So, okay, so the batteries then have to supply the current, the amplified current, if you want to call it amplified current, you have to supply the current, and that basically puts a constraint on the design of this power amplifier that the batteries have to do to supply the current demanded by the load. So, this gets into the efficiency of this circuit. How efficient is this circuit in delivering current to the load if it's basically taking a lot of current from the battery? So we'll work out an equation to calculate efficiency, but because of the way it's designed, this note just indicates that this amplifier is definitely not know that the extra current from the batteries has to be dissipated somehow. And, it turns out the BJTs are the ones that are carrying the current, so they have to dissipate the power, the current, which means that they can get very warm. And they have to you have to come up with methods to dissipate the heat from the BJT. And that's usually done with heat, what's called heat sinks. They're aluminum metal that attach to the BJT devices. So we're not going to really get into designing heat sink study. We just want to understand how do we actually design a push-pull amplifier. So this question of designing it, we noticed there are no resistors in the design. So the question of what is there, if we're going to design one of these, what actually do we have to go through in terms of a design process? Basically, we have to select the transistors. So if we want a 100-watt amplifier, then we go to some manufacturer's websites and we search for power transistors that can handle 100 watts. If we wanted 500-watt power, you're really getting into very high heat dissipation. So you're probably going to have to build something with aluminum heat sinks to cool off the transistors as they conduct large current. So designing it is not really calculating resistors, it's really calculating and specifying the transistor. And this term, dissipate heat without meltdown. Meltdown basically is when the transistor just PN junction overheats. And once the PN junction overheats, it does not return to its normal operating. So if you build a breadboard with BJT devices and you notice the transistor is getting very warm or even hot to the touch, then most likely you're going to have to change the device because the PN junction gets modified under very large heat. Power amplifiers are designed to basically dissipate a lot of heat. So this low power devices, you usually avoid using them in power amplifiers. Now the properties of the circuit, you have two types of input. There's AC input and there's DC input. And it's why you would want to amplify DC compared to AC is not really the subject here. We want to find out what's the maximum heat dissipation that these two transistors need to have. So if the input is DC, which is flat, if the input is 0 volts, right here, what is the output? So the input is 0 volts, what is the output?
Zero.
Why is it 0?
Kirchhoff voltage law.
Yeah.
The cut-in voltage hasn't been reached on either transistor.
Basically, the low cut-in voltage for this transistor. And the output is at 0. And once we go above the cut-in voltage, then the output will follow the DC on the input. Now, the equation for power is voltage times current. So if we want the power dissipated in this NPN transistor, we need the current in the collector, and then we need the voltage across the collector emitter. So it's just like a resistor to dissipate the heat. And then two types of power. You have instantaneous power and you have average power. In a DC circuit, these should both be the same. However, when you have other signals such as AC signals, and AC signals usually have a small incandescent power they dissipate in. So it's just voltage times current, and then we can write that in this form also, and then IO is D out over RL, so this is our power dissipation in the N transistor. Now if you take this equation and then plot it, and make a plot of it, and kind of make a crude plot so we show the actual plot. It comes out like a inverted parabola on this equation, which says that when the input signal is very low, right here, the collector emitter voltage is low. So we have very low power dissipation. And then when the input signal is very large, we have a large collector emitter voltage. But again, our power dissipation is low. So in worst case, power dissipation is in the middle of this curve. And then here's an example. It isn't an actual curve, it's just an approximation of the circuit. So the curve is basically indicating, go to follow the text. When the output V out is very small and zero, the collector emitter voltage is large, but the collector current is small, so the power dissipation in the transistor is small. And then when V out is very large over here, it's near the battery, the collector current is large, but the collector emitter voltage is small again. So again, we have very low power being dissipated. And this is almost where you have zero, very low input and maximum output. And it turns out this amplifier is most efficient when it's operating with its largest output, amplified power output, which is unusual because you would expect the efficiency to go down with the input becoming very large. So this point in the middle, when the output is about 1/2 of the battery, this is the worst case power dissipation. This is kind of the mid-range volume of this amplifier. And that basically is where the devices are going to heat up the most. And the equation, you take this equation here, so if we solve for V out, worst case, it's VCC over 2. So we take this, we can substitute this in this equation, and we come up with the power dissipation maximum NPN transistor is the battery squared over 4 times the load resistance. So if the battery is 10 volts, and that's 100 over 4 times whatever the load resistance. Now it's not unusual for these amplifiers to require voltages in the tens of volts. You can have 50 volt, 100 volt, even 200 volt batteries in order to deliver the output power. So these are still very popular power amplifiers, but they actually, you're going to develop very high DC voltages. You have to probably bring in AC transformers so you can step up the voltages. But this is basically the power dissipation in the transistor. And here's a simple example. If the battery is 10 volt and the load is 32 ohms, this transistor here needs to be able to dissipate 10 squared over 4 times 32, around 0.78 watts. And that's for the NPN. The PNP would need to dissipate the same, so you'd do about twice this. And now you would basically go online and search for the transistors. Yes.
Why is it squared?
In fact, that the lower part on this parabola take that equation, this is the power dissipation equation here, is equal to V out over RL times VCC minus V0. So the worst case is when V out is VCC over 2, so we take those and substitute it here. The V out also be substituted here. Do that on this equation at the bottom. The V out is still in there, but it's been replaced by VCC over 2. You go on paper and write out how to manipulate this equation to get this version here. And that's a little bit simpler equation than this earlier equation, but you should be able to plot this parabola. This is just one point on the parabola here, so this is just the power dissipation at this point right here. This equation is the entire parabola here. So this is just saying if I pick one point, what's the worst case power dissipation in the transistor? It would be this point. So that's where we get this equation from at the bottom. So arbitrary input signals, AC, square wave pulses, power dissipation is different from each type of signal. Now at the lower part, DC is the worst of all worst cases to use for this type of amplifier. So when you're deciding on the type of transistors that you want to use, you want to make a couple of calculations, one for DC input and one for AC input. So with that, you can basically make those calculations. And another one component here is if the input signal is too large, can the push-pull amplifier go into saturation mode? So you notice the batteries are 10 volts, and let's say DC set is 0.2 volts. That means its output can swing probably up to plus 9.8 and minus 9.8. That's 18 to 19 volts peak to peak. So if the input, if you say, well, I'll just disregard the saturation voltage, and then what would be the maximum input, you might conclude that the maximum input would be equal to the battery's level, 10 volts. And the reality is it's going to saturate when you get within 0.2, the output gets within 0.2 of either 10 volts or minus 10 volts. And again, does that really matter so much as a couple of tenths of a volt? Probably not. If you do a simulation, I believe it one of the homework 2 problems, they ask a question similar to this, how it actually responds to that. So, if the input signal goes above the battery, and this is kind of an ideal situation where VC sat is 0, and the transistors will saturate. So the idea of the input is, as long as we keep the input amplitude below the battery level, the transistor should be in the active mode. Now the large signal is small signal. What happens if this resistor is very small? And this node says 8 ohm speaker. So you're going to protect, using this for an audio amplifier, we're connecting to a very low resistance speaker. Now, 8 ohms was what we were asking for substantial current from the batteries in terms of the power to drive 8 ohms. And we have to take into account that the op amp can only deliver a certain level of current to drive this have to take into account the dial drop. Of course, the PN junction, the QN.
9.3.
So we have 10 minus 0.7, 8 ohm resistor, and then we can calculate the current in this resistor, in this 8 ohm speaker. And with that, we can decide if we're going to have the base current to drive an 8 ohm speaker. So if we disregard the drop in, and we're going to assume that if we drive this circuit hard enough, we can basically, worst case, rather than use dial drop, we just assume that we're going to get 10 volts out. So we're kind of over designing. And this is probably a good idea when designing, is to kind of over design. So this is just saying we'll keep in mind that there's a dial drop, but was at the same time, whoever is adjusting the amplitude here, it might increase this up to 11 volts a second. When we do that, the output will still get to 10 volts. Try to get to it. It's still not a practical case because you've got the DC stack. But it's an ideal case, the output is 10, the maximum current from the device. So the maximum current here is 1.25 amperes. So what is the issue at this point?
The maximum.
This is the load current, and this is the op-amp maximum output. So what's the issue with this design?
The output current max for the input current? Maximum.
Well, it's asking, can 25 milliamps and that drive 1.25 ampere? So you have your, and the transistors in the active mode, so we have I sub C is in the beta, I sub B, so you calculate the beta that you need for this setup to work. And let's assume let's assume that it works. The maximum power dissipation here is 10 squared divided by 4 times the 8 on the speaker, so it's 3.125 watts. That's the power the transistors would have to dissipate. And to the advantage of the designer in selecting power transistors, usually the betas on those transistors are low. And that's because the emitters, when these devices are designed, these emitters are designed very large, oversized emitters so they can help dissipate the heat. So this transistor we select online and the manufacturer provides normal beta is going to be 30, and we calculate the base current with basic beta 30. I sub B is I sub B over beta plus 1. Make sure you have this formula on your formula sheet. Because it's a quick way to calculate base current given I sub B and beta. So that's 1.25 amps over 31. So we need 40 milliamp from the op-amp. The op-amp can only deliver 25 milliamp. So what are your options at this point? And it's fortunate that you would check this because if you order large quantities of this amplifier, basically when we turn it on, it just simply wouldn't work because the op-amp could not deliver enough current. An alternative circuit then is called a Darlington amplifier. And this is an example of the Darlington push extra PNP device here. So this Darlington, this creates what's called a beta square configuration. Beta square. So if beta is 30, what is beta square? 900. So if beta is 900, we go back to our equation here, and beta plus 1 becomes 900 plus 1, and we find out that we need a much lower base current from the optimum. So the price, though, is we have to purchase, we still have to purchase the high-powered NPN and PNP devices, but this second NPN and this second PNP, these can be low-powered circuit cards. And circuit has something else added to it, and that's we basically are, even though we've studied op-amps, in order to build advanced circuits, you basically get to a point where you have to add op-amps or diodes into circuits with the BJT transistors. So this application is adding 2 op-amps. The middle op-amp, this is a comparator, and what it's doing is it's comparing the output voltage here with the voltage on its non-inverting input. When the input voltage here goes to 0, or when it goes through the cut-in voltage of the output sends feedback to the comparator to push current into the basis here. And what happens now is that helps to reduce or remove the crossover distortion for that circuit. And the these are from the problem sessions on Canvas for BJT amplifiers and MOSFETs. So this is a version from the push-pull amplifier section. So this question is, it's a push-pull amplifier. The emitter bases are 0.7 volts. If the base emitters are 4 bias, beta is 100, early voltage is infinite, and the batteries are 10 volts. So the question, if the DC voltage on the input, and you notice this is a positive side of the DC, is given. So the DC voltage on the input is given. The output voltage is minus 6. The output voltage is minus 6 volts on this point here, and the load is 600 ohms. So which transistor is on? So we have minus 6 volts on the output.
PNP.
And why would the PNP be on?
Because it's pulling.
Because
It's pulling current.
okay, so what's the input voltage if the PNP is on? This is kind of, when we work with these problems, we treat it like a diode, kind of project some type of reaction. That way we don't have to go through multiple attempts to solve the problem. So the output is minus 6. What's the input? D sub S input. PMP, because the emitter is the P type part of the PM junction, the input voltage has to be higher than the output. The input voltage is higher, is the output higher than the base or the base higher than the emitter? And that's what this question is. Which BJT is on, which one is on? And in order to get the volts current, it's always given if it's minus 6 volts on the output, just divide that by the load resistance, 6 on your own. But the last part says, what's the input voltage V sub F? Again, a TMP transistor, the emitter is 0.7 volts higher than the base. Again, is that correct though? So the output is minus 6. The base has to be 0.7 volts lower than the emitter. It's actually the flip of the NPN transistor. So the PMP, if the emitter is at minus 6 volts, the base has to be
Minus 6.
0.7 less than the emitter. And we'll make sure we got the polarity right. So that would say 0.7 less than 6. So it's, what is that?
Minus 6.7.
Minus 6.7 on the basis there. And if it's minus 6.7 on the base, the NPN is definitely off here. So we kind of projected what the result is here. So here, if the output is minus 6 volts, Q2, which is the PMP, is on. Q1, the NPN is on. And then what is the output voltage? So V out minus V sub S is equal to emitter base of Q2. And it says it is 0.7 because in NPN we refer to as emitter base, not base emitter. So that's minus 6 minus 0.7. So the source is minus 6.7. And then what's the load current? It's minus 6 over 600 ohms, which is minus 10 milliamperes. So we want to go back and review active mode for between PNP and NPN. PNP has just the reverse polarity of it. Now this question is asking, and we just basically went through this one. The same circuit, however, the input now is 0.1 volt. So which transistor is on?
Neither.
And the response here is 0.1 volts is less than the cut-in. Assume the cut-in is 0.5, so both transistors are off, and there's no need to put in the collector base emitter transistor is 0. We just take the load current is 0. For each BJT, is it on or off? V out is equal to 0. Now, that was a 10-point question. You definitely don't want to miss it, because we're not keeping track that diodes and BJTs have a minimal cut-in voltage. Usually this problem doesn't really say anything about cut-in voltage. You notice that it's expected that since we covered diodes already, we've already mentioned cut-in voltage, so the problems most likely do not say any mention of cut-in voltage. It's expected that you'll be aware of that voltage. And this is looks like it's similar to the first problem, except the input now is given as 5.5 volts. And the batteries are still 10 volts. So the input on the base is 5.5. What's the voltage on the out? And now you're forward biasing a basic input. What do you mean? So 5.5 minus 0.7. And then which BJT is on and which one is off? So which BJT is off?
And
So you have 5.5 positive on the base, which BJT is off? Q1 or Q2? And why is it off?
off.
Q1 is on, and Q2 is off.
And now we have to solve it with like a diode problem.
Because it's above the cutoff voltage for, cut-in voltage for Q1 and below for Q2.
Well, the cut-in voltage is Q1 and below. Basically, can't turn on Q2 because it's a positive voltage. And you can put in cut-in voltage also. And then load current, basically, you can solve from here. Now, what we'll do here, we'll look at these some more on our next session. Right now, we're just going to return the, let's see if we can return our exams here. The exams have 5 points automatically already added, and that's why we're putting a small +5 on there. So whatever mark is on your paper on Canvas, you'll find the 5 points have been added, should have been added on Canvas. And after the sitting here, we'll go over a quick review here of the exam, but if you have questions regarding the exam, keep in mind, since 5 points have already been added, if you find something that's worth 3 points or 4 points, there's no need to discuss it because 5 points have already been added. If you find something 6 points, that means there's an extra point to be acquired. So keep that in mind. Everyone, okay. Now, it's unlikely to find something that's substantial, basically it's your work, so you'll need to review it. Carla De La Cruz. Come on. Hugo Gomez. Allen. Alexander Garcia. Clinton Ford. Antec Senior. Kevin Diaz. Judison. Giovanni. Aaron Arnold. Kenzie Henry. Eoin. Madison. Richard Gonzalez.
Sorry, so you said no?
Eoin
Oh.
Nash. Tyler. Ace Bowen. Wayne Hart.